Okay, so hi everyone. Thanks very much for turning up outside official lecture weeks. So I hope it's worth it. I should say, I know I promised last week 0 equations. I did look at the slides and I couldn't resist putting in just a couple. So I hope you don't kind of feel like resentful that you actually turned up and then like really showing you an equation after all. So this lecture, we're really going to focus on, I think, one of the big success stories of reinforcement learning. And I hope to persuade you that not only is it an interesting testbed for understanding reinforcement learning, but it also will help you understand really how to make progress in a large set of interesting games, which I call classic games, games that people have played for many, many years and particularly popular. So there's a fair amount of different kind of areas we're going to try and go through. But I really want to focus this lecture on what I consider to be the state of the art. So this is a little bit different to some of the other classes, and really my goal is to show you actually how to put together everything we've seen in the rest of the classes to really achieve state-of-the-art performance. And so what I'll focus on is not, maybe the canonical examples of reinforcement learning, but rather what's actually worked, what's worked really well in these classic games, so that you can actually understand, at least to some level, what's been used to reach superhuman performance, for example, in certain games. To do that, I've put in just a little bit of game theory, very minimal, just to help understand, what it means to do reinforcement learning in this setting, what it means to even talk about optimal behavior when we have more than one agent involved in a situation. And then we'll focus on minimax search, which is a special case for two-player zero-sum games, which is the main class of game that we're going to consider in this lecture. Then we're going to talk about really how you achieve performance. Now we're going to talk about reinforcement learning by games of self-play, agents that just play themselves again and again and again, and then can go off and beat the top human players in the world. That's our goal. We're going to talk about how to combine these sorts of planning ideas, minimax search, high-performance search engines, with reinforcement learning. And finally, we're going to focus, if we have time, I'm not sure if we'll have time for that, on some recent successes in imperfect information games. So this is games where there's hidden state, like card games, like poker. And if you want to go out and build a poker bot to beat the world's best players, then here's the recipe. Okay. So, state of the art. So I just want to start by saying, why should we care about this lecture? Why study games at all? I mean, I know a lot of people think, well, games are a little bit, fun or trivial, or why is it an interesting test bed? And I think actually there's a lot of legitimate reasons to really focus on games. First of all, they tend to be the examples that we have, which have the simplest rules but the deepest concepts. I mean, that's how games are designed. They're designed to have rules that you can read in just a paragraph or two. And yet, the actual gameplay concepts which get involved, require hundreds of years of study for people to become very good at a game like chess or Go. So that evolved over hundreds of years how people play these games. And also, I think we can say that games kind of give an IQ test for artificial intelligence research. So if you know how you're doing a game, you can really benchmark yourself not just against other games by playing in tournaments or computing your rating against other games, but also against humans. So we have these humans who've devoted their lives to playing games, and now can really match up our computers to a human in a domain where a human is really dedicated decades of their learning time to this, and really at the pinnacle of what we consider intelligence. So for those reasons, a long time ago, back in the day when AI was sort of coming through, a lot of people focused on games, in particular chess. And chess was called the Drosophila of artificial intelligence. Now, Drosophila is Latin for fruit fly. And the reason that chess was called the Drosophila is because, just like in genetics, the fruit fly was used as this very easy case study for running lots and lots of experiments. And so you can find hundreds of papers on the fruit fly because it's kind of particularly simple and just became the natural test bed that everyone looked at to understand the deeper concepts. So chess became the Drosophila of AI. And then at a certain point, as we'll see, chess kind of was solved in the sense of achieving superhuman play. People moved on to other games, Go and so forth. And I think also these games, they kind of, although they're very simple, you can think of them as microcosms. So there's some interesting issue that we might care about in the real world, like hidden state. And then you can look at a game that basically simplifies everything else down to very simple rules, but still looks at the situation where you have hidden state. So it gives us a way to understand these in rich but simplified settings. So, that's all very well, but I think, games are fun, so let's have fun today and hope you enjoy finding out about these. That's the real reason, of course. Okay, so This is the one slide I kind of want you to, 2 slides actually, I want you to really get some understanding of how far we've come with reinforcement learning. So this slide here shows, for all the methods that have been tried in these classic games, all of AI, what has been effective. And so basically what we're looking at is different domains here, so checkers, chess, Othello, backgammon, Scrabble, Go, poker. So it's a selection of the classic games we're going to talk about today, some of the biggest and best known games. And this is the level of play that has been achieved by artificial intelligence systems in those domains. So perfect in checkers means it's literally been solved, the game has been solved, so this checkers program. Chinook can play perfectly against God. Superhuman means it's defeated the world's best human player. And then we've got some things which roughly play at, say, what we might consider grandmaster level now. These Go programs play about 6 down now. So that's roughly the level of the best players in Europe. So all of these successes are very powerful, but I guess what we want to know is how far can reinforcement learning get? How much of this has been done with RL? So this slide shows now the same information, but just for methods which are based on reinforcement learning. And what we've looked at now, so now these are reinforcement learning programs to achieve this level of performance in these games. And in each case, I'm looking at the program that's like the first to reach that level of performance, so like the first program to reach superhuman level. And what we see is highlighted in red are the overlaps with the previous slide. So I guess 5 out of 7 of the examples we're looking at were achieved using reinforcement learning, and the 2 which are in black aren't the best examples in their domain, but they still come an awful long way. So in poker, there is now a superhuman, probably superhuman reinforcement learning method. In chess, it's perhaps surprisingly, despite being the Drosophila of AI, it seems that RL, it turns out, has got slightly less far on that one, but still reached international master level, as we'll see. So reinforcement learning can achieve really high performance in all of these games, and is basically the primary mechanism by which success has been achieved in classic games. Okay. So let's talk about game theory. So we want to understand the ingredients that get us here. What's common about these different programs? What were the methods involved in reinforcement learning that we can understand and use, and then go off and use them not just in games but in other domains? So that's really the goal here, is to distill out the essence of what was important in all of these success stories, and then understand those success stories, internalize them, take them away, and be able to do that in any domain you work on. That's the goal. Okay, so let's start by game theory and just understand, what do we even mean by a game? So there's a question which we should be asking ourselves, which is, what does it even mean to make an optimal policy in a game? So in an MDP, all the cases we've looked at so far, single agent domains, it's very clear what optimality means. You just want to maximize your reward in that game. But the optimal policy for the ith player depends on how all the other players play. So that should be clear, that if you're playing rock, paper, scissors, and I'm playing against someone who always plays rock, my strategy, the optimal strategy against someone who always plays rock, is very different to the optimal strategy against someone who always plays paper. They're totally different strategies to win against these games. They're both optimal in some sense, but what do we really mean by the best policy amongst this whole space? So we're going to talk about this superscript we're going to use to represent the player number here. So we're going to have a policy for each player. So the policy is just the familiar policy we've had before, where there's some strategy for picking actions, but each player has their own strategy for picking actions now. And so we're going to talk about something. Let's first of all consider something called the best response. So let's consider the case where I'm in a game and all the other players fix their policies. So if I was playing against fixed opponents, I could ask the question, what's the best way to play against those fixed opponents? So for example, if I was playing rock, paper, scissors, and I was playing against someone who always plays rock, then the best response to that strategy is to always play paper, cover up the rock. So that's the best response to a fixed opponent, someone who always plays in that way. And in multiplayer games, this also applies. You can have the best response to a whole set of different policies, as long as those are fixed. And so this, in some sense, reduces the game to the case we're familiar with. We can just treat all the other players as part of the environment. and then just find the optimal policy against that environment, which includes the way that all the other players are going to play. But this doesn't really help us understand, what the best policy is overall in this domain. We want to understand, well, I don't just care about how to play against this particular opponent. I want the best way to play in this game. So can we come up with a better criteria? And the most famous criterion, in fact, it's probably one of the only things I've talked about in this course, which is so famous that you can find Hollywood movies about it, right? The Beautiful Mind. The Nash equilibrium is basically the main game theory concept for talking about optimality. There are others. I'm going to focus on Nash equilibrium. And a Nash equilibrium is basically a joint policy for all players. So it's a way to pick actions for all players, such that every single player is playing a best response to everyone else. So if you find a Nash equilibrium, it basically says that my policy, if I'm player I, my policy has to be a best response to the policies that everyone else is following. And so that means if we're playing rock, paper, scissors, then my response, the way I play, has to be a best response to my opponent, but the way he plays has to be a best response to me as well. So it can't be the case anymore that I just always play paper, because if I always play paper, he would be able to play scissors and defeat me all the time. So I wouldn't have the best response then to his new strategy, which is to use scissors all the time. So another way to say this is that when we're in a Nash equilibrium, it basically means that no one would choose to deviate from that strategy. So what is that? So in rock, paper, scissors, that means everyone plays 1/3 of the time rock, 1/3 of the time paper, 1/3 of the time scissors. That is the equilibrium strategy. If everyone is playing that strategy, no one would choose to deviate from that strategy. If they did deviate from that strategy, someone else could find a way to play that would exploit that and would be a best response to that strategy. So in the Nash equilibrium, no one would choose to change their strategy. This would be the best thing given everything else that everyone else is playing. So it's something that's like a happy medium amongst all the players. It's like at that point everyone can say, okay, we all think we're playing the best way according to what we're observing of everyone else, according to these strategies that we know about everyone else. Is that clear as a solution concept? Okay, so we're going to use this as like our gold standard for what it means to achieve optimality in games, the Nash equilibrium. If we can find a Nash equilibrium, we'll sort of declare victory and say, that's the best we can do in some sense in this game. It doesn't mean we found the best response to a particular opponent. It just means that we found some strategy which, in some sense, dominates all other strategies against equivalent ways to play, against any other way for other players to play. Okay, so let's talk about reinforcement learning now. So if we come back to the best response, we can think of the best response as the solution to a single agent reinforcement learning problem. So best response, we can just treat the other players as part of the environment. We take our other player, we push them into the environment. I can imagine I'm playing rock, paper, scissors, where I'm just a single agent in an environment where I happen to be playing some game where there just happens to be some other player who's playing against me, and all I see is, their action is what I observe, and I get to pick my action. We can just treat that other player as part of the environment. We can do all our familiar things that we do when we do reinforcement learning. We can treat that as the environment. We can make an MDP out of rock, paper, scissors or any other game. And now, the best response is just the optimal policy for that MDP. So we know how to find best responses. It's basically you create an MDP that represents that game. You fix the opponents. That defines the environment for your MDP, defines the transition dynamics. And you push the opponent into the transition dynamics of your MDP. And then you just solve for that MDP. But the Nash equilibrium is a more powerful solution concept. It tells us something a little bit more profound. It tells us generally about any way to behave amongst all different joint policies amongst all players, which is the best in some sense. And so the way to understand the Nash equilibrium, how can we find this by reinforcement learning? Well, the Nash equilibrium is a fixed point of self-play reinforcement learning. So what I mean by that, so what do I mean by self-play reinforcement learning? I mean, imagine the case where I am in control of all the agents in my game. So I'm controlling player 1 and player 2 in rock, paper, scissors. And I get those agents to play against themselves. So self-play, I'm just trying my own policy against some other policy. I'm controlling this thing. So I'm controlling the policies, I'm learning these policies, and I'm getting them to play against each other by self-play. And so we generate this experience, and we treat that as our experience. And given that source of experience, we want to learn the best response to other players. So if we're in an environment where we're seeing the responses of all the other players, then we're basically learning a policy that's adapting to how all the other players are playing. So we're learning by self-play. We're seeing how the other opponents are playing. We're imagining that the other opponents might play in a certain way. We're adapting. So as my opponent gets better and better and better, I have to adapt and find better and better counter strategies. And then my opponent has to find better and better counter strategies to those. And we keep adapting the policy by self-play, imagining these games, playing against each other. And the point is that if we ever reach a fixed point of this process, which by the way is challenging, it's not clear that all RL methods converge when you try and do this. But if we do find a fixed point, if we do find an optimal policy at any point where all players declare that they found an optimal policy to the behavior that's generated by these other players, that is a Nash equilibrium. So we just have to solve for the RL problem, which is generated by the play of the other players. If we can solve for that RL problem dynamically adapting this thing, and we find a fixed point, we will arrive at a Nash equilibrium. And there's a nice seminal piece of work by Michael Lippmann I'm not going to talk about. This was in his PhD thesis, where he showed that basically for a large class of standard reinforcement learning algorithms, they do actually converge on the Nash equilibrium, at least in the table lookup case. So it's not impossible to do this. It's, if you use your favorite algorithm, there's a good chance that you really will just converge by self-play to finding this Nash equilibrium, the best way to respond to how your opponent's playing. So it's like an iterative process. We just start playing games against myself. I improve my policy. Each time I improve my policy, I'm changing the way in which experience is generated. I'm changing the RL problem a little bit, and I have to adapt to that until I become better and better and better and better, until if this process actually stops and reaches a fixed point, it's the Nash. Okay? 2 questions. Good.
So is the Nash equilibrium, will that be unique? It exists.
Okay, good question. In general, no. For general games, it's not unique. For the class of games we're going to consider, there is a unique Nash equilibrium. So we're going to consider 2-player zero-sum games, which do have a Nash equilibrium in the least imperfect information case. So most of this lecture will talk about the case where there is a unique Nash. That's not always true. So in a game like poker, for example, there's a whole family of different Nash equilibria. There are many, many different ways to play a Nash. Some of them you might consider better than others because they might generalize to play better against tutors, for example. Was that the same question?
No. I was just going to check that I was understanding correctly. So this best response is like what we were doing for our homework. We've incorporated the dealer into our environment, but with Nash equilibrium, we could get to learn the dealer's best policy as well.
Exactly.
Okay, cool.
Yeah. So this would, if we took the Easy 21 assignment and we now learn the dealer's policy at the same time as we're learning our own policy, and the dealer would be adapting to how our policy is improving, and we'd be adapting to how the dealer's then improving, you would find the best joint policy. And so that would then tell you how to play not just against that fixed dealer, but potentially against any dealer, because you've learned something which is a much more powerful solution concept that tells you about play in general in this game. Good, thank you. Okay, so we're going to focus on a special class of games. So game theory considers many, many games. We're going to consider 2-player games with 2 alternating players. So they actually take turns. And we're going to call these players arbitrarily. I'm going to call player 1 white and player 2 black. Just think of that as a naming convention. Again, it could be games which don't even have colours, that's fine. And the idea is that white plays, and then black plays, and then white plays, and so forth. It's not simultaneous games for us. And we're also going to consider zero-sum games. So zero-sum game basically means you've got equal and opposite rewards for both players. So if something's good for black, it's bad for white. So if something's good for white, it's bad for black. So it basically means, that every time we're in a situation, there's a very clear definition of what it means to do well in that situation, because both players are fighting in exactly the opposite direction. They're never trying to cooperate to achieve a common goal. And we're going to consider how to find Nash equilibria in these types of games, these two-player zero-sum games. We're going to consider two general methods for achieving this. One of which is like a planning approach. So if you think of the two main families we've considered in this course, we've talked about reinforcement learning, we've talked about planning. So we can start off talking about the planning approach, like game tree search. We basically build a big search tree to find the equilibrium solution. And then we're going to talk about self-play reinforcement learning. So methods that just do TD, for example, to find this solution. Okay. And we're going to break this up into perfect and imperfect information games. So perfect information, also known as a Markov game, is fully observed. So you see the entire state of the game. So chess, checkers, Othello, backgammon, Go, these would all be examples of perfect information games. So note that you can still have stochasticity in these games, like in backgammon there's a dice roll, but you see everything. You see the full state of the game. You get a Markov state. In contrast, an imperfect information game is partially observed. So if we think about Scrabble, you don't see the letters that your opponent has on your rack. And in poker, you have a much more serious type of imperfect information where you really don't know what your opponent's cards are, and that really affects how you need to play the game. Okay, and we're going to start with perfect information, spend most of the class on perfect information, and then we'll just spend a little bit of time at the end on these games. Okay, so we'll start with minimax search. So let's get back to our familiar territory of RL and see if we can kind of build up those basic building blocks again in the world of games now. So we want to understand what it means to have a value function now. So a value function we can define in the natural way, which basically means the value function is going to tell us the expected total reward given policies by all players. So we're basically looking at these two-player games. We're going to say there's a policy for black, there's a policy for white, and what we want to know is if black plays in a particular way and white plays in a particular way, how much reward will there be at the end of the game? And we don't need to estimate the value function separately for black and separately for white, because this is zero-sum. We know that what's good for black is bad for white, so we can just negate it to get it from the opposite player's point of view. So we just need the one value function, and that tells us, under this particular way of playing for both players, who's going to win, basically. So we can always think of this reward, so there's the return now. Okay, in general there might be games where you have some reward per time step, you might have discounting, you might have all the other things we have in RL, but the normal case in games is there's no reward, no reward, no reward, no reward, no reward, and then at the end of the game someone wins. And then we say that's either a reward of 1 or -1, depending who wins. So that's the standard case we consider. So this then basically tells us, this expectation is who's going to win. What's the probability that black will win this game if both players play in a certain way. And now what we really want to know is, well, what's the best way that both players can play? So if we consider the whole space of different policies for both black, for both white and for black, what's the best way to play? And so the minimax value tells us these best possible values. In other words, if white's trying his hardest to maximize the score, and black's trying her hardest to minimize the score, then what will the score be if both of those players are playing in that way? So that's the minimax value function. So this is like a fundamental concept of both game theory and in practice just building any high-performance game system. It's the standard tool is to do try and find this minimax value function. And so we really want to know, what are these V stars? And again, just like usual, if we have the optimal value function, we're pretty much done. In a game, in particular, if we have the optimal value function, we know how to play. This tells us, what move we should really take, because we know how to pick a move for black or for white once we have this V star. So a minimax policy then, so if we come back to policies, so minimax policy is any joint policy, any way to play for both players that achieves these minimax values, and achieves the best possible score from white's point of view and the lowest possible score from black's point of view. So both players are striving their hardest to kind of fight against each other and maximize the probability that they'll win the game. And then at the end of that process, that struggle, we want to look at the policies that basically achieve that best possible outcome, and this is the minimax policy. And the value function tells you basically who will win from any state if they're struggling in this way. So another way to say this, under perfect play by both players, if they assume that the other player is playing perfectly against them, then who will win under perfect play? That's basically what this is saying. Now, to answer the question from earlier, in this setting where we have perfect information, 2 players, zero-sum games, there is a unique minimax value function, and the minimax policy that's defined by that minimax value function is always a Nash equilibrium. So it's a very nice special case where just by computing this minimax, you also find the Nash. This is the Nash for these games.
So can I ask a question?
Yeah.
So I'm not clear in my head why it's max and then min rather than min and then max. So yeah, why is it max over pi 1 of min over pi 2 and not min over pi 2 but max over pi 1? What is it?
Let me try and make that clear in the next slides. I think that's going to become clearer. So I think the right way to think of it is it's a nested process. Like whoever's to play first, so if white's to play first, then it would be a max for white first, and then a min for black, and then a max for white, and then a min for black, over all of the actions which are taken over that sequence of steps. That's kind of a shorthand for that, basically. And so we have what we call minimax search, which is the standard way to estimate this minimax values. And so the way to do this is to build your familiar search tree. So if you open any AI textbook, they might not tell you all the slides which came before this, but probably chapter 1 will be this. Right? Chapter 1 will be how do you do minimax search. And the idea is to basically build a search tree where if you're playing tic-tac-toe, noughts and crosses, whatever you want to call it, you start in some position, you consider how white, which in this case is x's, might play, and then you consider all the way that the black, in this case circles, might respond to that. We build the complete search tree, and now we analyze this search tree to figure out what actually is the optimal play by both players, looking at this whole search tree. And so this process of game tree search, you can actually search from this root position to figure out the minimax values. Turns out that this was actually first introduced by Claude Shannon, who's the father of information theory. So in his spare time, he basically introduced the whole of game theory and minimax search in this programming computer for playing chess, which was the first ever chess program, which actually ran on paper because he didn't have a computer to run it on. So he ran it on paper, but it was a valid chess playing program and had a lot of the main concepts in there already back when he developed this. And so if we just run through this very briefly, we can think of this as like some game. So let's consider some game with 2 players, which we'll call max and min. So this is like the, I guess the colours are swapped from what we were talking about, which is a little confusing. But the idea is that there's one move for max, then a move for min, then a move for max, and then we basically get some outcome of the game. Like this is the score at the end of the game. And the question is, what's the real score from the top node, from the root node, if everyone plays optimally? If max plays to max at every step and min plays to min. And so this can just be computed in a brute force fashion by doing some kind of search. So imagine we were doing, say, a depth first search. We go all the way down to the leaves, and then we back up this information. And that's the standard approach to minimax search. You do a depth first search. You come down to here. You see a +7 here and a +3 here. So you would say, aha. If max is trying to maximize amongst these values, this node here must have a value of +7, because max gets to choose whether to play here or to play here. And similarly, max gets to maximize amongst these. We see that we've got a value here of -2, which is greater than -4, +9, which is the max of these two, and -4 is the max of these two choices. And then we iterate and we say, okay, well, from min's point of view, we want to then minimize these things. So min gets to choose amongst these actions B1 or B2, and so min gets to choose this action B2, which leads to -2, rather than this +7, which would be great from max's point of view, but a disaster from min's point of view. And similarly, here we've got a choice between -4 and +9, so min chooses to go to -4. And so now we can see from the root, there's one final decision from max. This is the first decision in the game that gets made, and now we can understand what that first decision should be, because max clearly would prefer to go and choose A1 rather than A2 because it has a higher value of -2. So this is minimax search. It basically gives you a way to compute not just the optimal values, but you can see also now the optimal policy as well. So the minimax policy would be to pick A1 from this root node for max and so forth. So you can see that if we can do this search, we're basically done. We've got optimal play. We've figured out how to do this. And there's only one problem, which is that this search tree in any game of interest is vast. Like it just blows up exponentially with the depth of the game, and typically you can't solve the whole search tree in this way. So in practice, what we do is we, instead of going all the way to the end of the game, we basically truncate the search after a small number of steps, and we use a value function to summarize, to estimate the minimax value from that node onwards. And so if we have this value function, which is in game tree search referred to as an evaluation function or heuristic function, but I think we, in this course, can correctly understand it as a value function. It's something that's trying to estimate the true minimax value. If we have that estimate of the minimax value, so we've got some value function approximator now that's trying to estimate the minimax value. So this could be our familiar function approximators, like a linear function approximator, a linear combination of features, or a neural net. And we've got this value function now. And what we can do is basically, imagine now we've got a game that goes on for 1,000 steps instead of 3 steps. What we can do is we can search down, consider the first 3 actions that we might take, build a search tree over those first 3 actions, and then in each of these leaf nodes, after 3 actions, we basically truncate, and we insert our value function here. So this might be the estimator that comes out of our value function approximator. Our neural net says, aha, this position is worth +7, this position is worth +3, and then we back up those estimated values all the way to the root, and we get an improved estimate of how to play the game. And so that is the standard approach to minimax search, which is used in every classic checkers playing program. And what I'm not going to talk about today is how to make this efficient. So, several decades of research went into making efficient minimax search, principally based on a method called alpha-beta search, which is just a way to cut off parts of the search tree which are guaranteed to not be interesting to either player, because we know, for example, that certain parts of this tree will never be visited because of the way that we're maximizing or minimizing. We can cut off large parts of the tree. So that's alpha-beta search, the most efficient minimax search, and there's decades of work on how to extend and improve this. Okay. Is that clear to everyone? Good. So what I want to do is just really make this concrete. So I'll give an example using chess, which is that canonical example where minimax search has been effective, and show how a typical chess program would actually build a value function to use in this minimax search. And so the way that this works is we typically have some position like this. This might be the chess position. And so most chess programs, what they do is they build a binary feature vector, which basically says, things like, do I have a white rook in this position? Yes or no. So if I do have a white rook, which I do in this position, that feature will have a value of 1. Do I have a white bishop in this position? Yes. Do I have a white pawn in this position? No, that has a value of 0. Do I have a black rook in this position? 1. Do I have a black bishop here? 0. Do I have a black pawn? 0. So that's kind of your features, just indicators saying, for each of the initial pieces that you have in the game, are these actually present in the position? And then what we have is a value saying how good is it if you have that piece. And this is familiar to every beginner at chess, gets told, well, rook is worth +5, bishop's worth +3, a pawn's worth +1, and then we just reverse that for the opposite sign for the opponent. So if the opponent has a rook, that's -5, -3 for opposing bishop, -1 for a pawn. And now we can evaluate this position just by taking a dot product of these 2 vectors. Our feature vector here, our binary feature vector here, and our weight vector here, which basically says how good is each of those features. How good is it to have a bishop, or to have a rook, or to have much more complicated features as well? How good is it to have an exposed king? How good is it to have a knight on an outpost? How good is it to have a particular pawn structure? In a typical program, we'll have thousands of these features. Each of them gets a value, so maybe not just +1, -1 for pawns, but maybe +0.002 for a particular pawn structure. And then you can just evaluate a position, and this is very, very efficient because you don't need to consider all of the features which are in your feature vector. You just look at the ones, and you just sum up the weights of the things which are actually in your current position. So you just add the 5 for this rook, +3 for this bishop, -5 for this black rook, and that gives you your position. It says, aha, the value of this position is 3. Then if you want to convert this into a probability of winning, we typically just pass it through a logistic function. So I'll kind of assume something like that is done at the end for most of these games now. So you can kind of squash that back down to a probability of winning if you want. Okay. Is that clear? Good.
So how about their location? Like, is it not important?
Sure. So you can make this as rich as you want. So you normally have the piece value. The piece values are like the primary raw information that gets used to evaluate a position. That's what beginner chess players use. Computers then use what are called p-square tables, which says how good is it to have a rook in this particular position on the board. And then they use much more complicated features still. You can look at conjunctions of different pieces in different positions. And if you look at recent shogi program, there's a shogi program I'm not going to talk about called Bonanza, and it's finally reached like human grandmaster level in a much more complicated variant of chess. And it uses something like 10 million different features, each of which is like some conjunction of different pieces in different positions. So you can make this feature vector very, very large, but the idea is just the same. I mean, it's exactly the same approach. So let's take an example of this. So let's look at Deep Blue. So Deep Blue, possibly still the most famous game-playing program. So what did it do? Well, it had 8,000 handcrafted chess features, so the learning process was really done by humans there. So these features were learned by humans, and the weights were largely hand-tuned by human experts. So there was a team of human grandmasters figuring out, how good is it to have this particular pawn configuration in this position. But it did use this binary linear value function, and then combined that with a minimax search, which was a high-performance parallel alpha-beta search on these specialized chess processors, which back in, I guess this is 18 years ago now, it was already searching 200 million positions per second and was able to look ahead, in some situations, up to 40 moves into the future. So it was a very powerful search. So these minimax searches, when you combine them with all these extensions, can give a great degree of effectiveness. So the results, well, Deep Blue defeated Garry Kasparov, who was then the human world champion back in 1997. Although this was probably a premature victory for computers, because actually Garry Kasparov got a bit daunted by playing against a computer and made uncharacteristic blunders. There probably should have been another 4 or 5 years of research in computer chess before computers really were better than humans. But this has gone down in history as the moment where it really happened. It's absolutely the case now that the top computers are way better than the top humans. And this became the most watched event in internet history. So it was kind of a big deal when it happened. Okay, but no real learning, no reinforcement learning. This was a case of handcrafting combined with a systematic minimax search to compute this minimax value function with respect to a handcrafted value function. Okay, a second success story I want to talk about is a program called Chinook. So Chinook is a checkers playing program. It again used a binary linear value function. In this case, it had a much smaller number of features, which basically said how good is it. So checkers is a game of drafts. I'm sorry, I spent too much time in the US and Canada. So basically it has these 21 features that basically describe where the checkers are on the board and what configuration they're in. But it divides up the features into 4 different phases of the game. So you can essentially have different weights if you're in the opening or the middle game or the end game. And initially these were hand-tuned, but we'll see later how reinforcement learning was applied successfully to Chinook. It actually outperformed the hand-tuned version, which was a nice result. But again, it used a high-performance alpha-beta search, and on top of that, it used this kind of backward search from the end game as well. So it searched backwards from one position, so it wasn't just a forward search from the root. It also searched backwards, where it basically said, if we know that this is a 1 position, let's back up 1 step and find all the places that we know can lead to a 1 position, and then back up from there again to find all the moves that can lead to a 1 position after 2 steps. And you can basically figure out then, by doing this retrograde analysis and backing up from 1 positions, you can consider all the simplified games with a small number of checkers, and you can play perfectly then from the last n checkers, where n, I think, goes up to about, in the latest results, I think about 11. So whenever Chinook got down to a situation with 11 or fewer checkers on the board, it was able to play perfectly without any search, without any. I just looked up in this table, what should I do, and it already had the result without doing any dynamic search. And so the results, well, there was this guy called Marion Tinsley, who was probably the greatest games player for any game in the history of games. He only lost 7 games in his entire career of playing checkers. So he played hundreds and hundreds of games, and he was just almost unbeatable. 2 of those games that he lost were against Chinook in a World Championship game to decide whether humans or computers ruled in the game of checkers. Unfortunately, the match was inconclusive because Tinsley had to withdraw for health reasons. He actually died before they could have the rematch. And so this led Jonathan Schaefer, the maker of Chinook, to say, well, how can I really prove that, if we can't play against Tinsley anymore, how can we really prove that we could have beaten him? And he decided, well, the only way to do that would be to show that he could play perfectly against God. So he went on this mission and eventually solved checkers in 2007 and basically built such a large minimax search that it was able to search to the end of the game and figure out perfect play in this game. So it's not a small game. It has something like 10 to the, I think, 24 positions in the game. So this was a fairly substantial undertaking, but it was possible to solve checkers. It's not possible to solve larger games like chess, Go, and so forth. Okay. So that just gives you some background in search. And I think it's really important to have that background because I think when we talk about machine learning and reinforcement learning, I think people have a tendency to forget the importance of search and planning. That there are domains, in particular these games domains, where search is the primary driver for achieving better performance. And I think it's very easy to go back into this mindset of, well, I'm just going to learn my value function and then I'm going to use it, or I'm going to learn my neural net and then I'm going to apply it, or I'm going to tune these weights and then I'm going to apply them. Whereas in practice, games in particular are an example where you really need to dynamically assess the situation and figure out, from this position here, what precise tactics should I follow to be in order to be able to achieve maximum performance. And so what we're going to look at is self-play reinforcement learning, but with a view to then combining this research in the next section. Okay, so let's start by going back to our familiar methods for reinforcement learning and asking, can we just apply these in a self-play context now? And happily the answer is yes. There's almost no change necessary to take an RL algorithm and apply it in a self-play context. We just change the definition of the game to be self-play. There's now, we're playing for both players. And so we estimate the outcome of the game, this return GT, is just who won the game. And then all we do is, if we're doing Monte Carlo, well, we update our weights of our value function approximator. We update our weights a little bit in the direction of the error between who actually won the game and who we predicted would win the game. And then this tells us the gradient, how to adjust our function approximator to achieve that difference. If we're using TD0, then what we're going to do is we're going to consider the case with no intermediate rewards, so you just get 0 reward, 0 reward, 0 reward, and then you either win or lose the game at the end. So it looks a little bit simpler than our usual TD update. What we basically say, what we're going to do is, before I play the move, I'm going to have some prediction of who's going to win, like I think black's going to win. But then I take a move and I figure out, actually now I'm in a situation where I think white's going to win. That generates a large TD error. So we say, actually I should have thought that white was winning all along. That's the error. We update the weights of our value function approximator, this estimator of the minimax values. We update that a little bit in the direction of the error between who I thought was going to win and who I then thought was going to win. And again, we have the gradient that tells us how to achieve that change. And we can do the same thing with TD lambda using the lambda return. So all our familiar machinery from previous reinforcement learning lectures is applicable in the self-play context. We're just trying to estimate these minimax values instead of the standard value function. And we're doing this in a setting where when we improve the policy, we improve the policy for both players. We don't just improve it for one player. We're trying to do this co-adaptation. So the policy improvement process becomes a policy improvement for both black and for white, so that we kind of get closer and closer to minimax, closer and closer to this Nash equilibrium. But functionally it's the same algorithm. You don't even need to change the code from what you were doing in a single agent setting. Okay, So one thing which often is different is this idea of using after states. So we often are in the case in games where we have deterministic games with known rules, where we know the rules of the game, and what happens from my move has some deterministic successor. Like if I'm in some position and I play a particular action, there's some deterministic next state I'll end up in. Like if I play, move my knight in a particular way in chess, I know exactly what position I'll end up in. So in this case, we can define something called the after state, which is basically a way to think about the value of actions without having to explicitly reason about Q values. So what we can do is, instead of representing Q values, we can say, let's just look at the value, so that the optimal value, and we want to know which action is the best. And so to do that, we need to look at the action values. We need to say, well, if I'm in this position, should I move my knight here or my queen over here? Those are the different actions I can take. And so all we need to do is to look at the successor position that I would end up in if I actually took that action from that position. So I consider each of them separately. I look, let's take that move the knight over here, look at the position I end up in, we call that the after state, evaluate that after state, and now I just need to look at the after states of all the actions I could take and pick the one with the highest value. So we can do this because the game is deterministic and we have and we know the successor function. So we know the rules and we know what this will take us to. So we can very efficiently figure out what the best move to play is. And then the only thing we do, which is slightly different, is that instead of just maximizing when we do our policy improvement step, we maximize for white and we minimize for black. So this is just like in our minimap search tree, we want to maximize from one player's perspective but minimize from the other player's perspective. And so when we actually take our policy improvement step, all we do is we basically consider all, so from white's point of view, if white's going to play a move, we look at all the after states after all of white's moves that it's considering, and we pick the one with the best value. And from black's point of view, we look at all the moves that black could play, and we pick the one with the lowest value. And this is a way to improve the joint policy for both players. So this is a way for black to make pull the score down, and for white to pull the score up. And if you keep doing this, this is the thing which, in principle, if you have the right algorithms, will converge on the minimax values by self-play alone. We don't need to build that big search tree. We just do our math. Okay. So let's look at some examples. Let's get into the details of when has this been successful. So I want to talk about perhaps two of the best known games where self-play has been successful, in Othello and in backgammon. Backgammon example is particularly well known, but we'll start with Othello. So Othello is a game, probably most of you know it, but it's a game which looks something like this, and you have black and white counters, and what you have to do is place, if you kind of place, if black has placed a stone here, it would turn these two white counters, which are kind of caught, pincered in between those two black stones, would be flipped over to black. And so the game proceeds in this fashion, flipping over stones until at the end of the game you see who's got the most stones of the right colour. And so this is a very tactical game, but it turns out that it's possible to build a value function that performs quite well in this game. And the way that Logistello did this was to basically, instead of like in Deep Blue where all these features were handcrafted, what Logistello did was it basically discovered a large vector of binary features. So it built a binary feature vector containing 1.5 million features, and those features were basically configurations of stones which occurred commonly in the games it was playing by self-play. So if it was playing in all these games, you would kind of look at it and say, okay, let's consider, say, a configuration of 3 by 3 stones in the corner, and let's make a feature for each pattern that can occur in this 3 by 3 corner that actually occurs in real games. So there's a feature that kind of says, does this configuration of stones occur in this corner? If it does, the value of what the feature would have a value of 1. If it doesn't, have a value of 0. And now we have a weight that basically says, how good is it to have a corner that looks like this? And you add together all of these different features. And basically what Logistello did was it discovered all of these different features within particular pattern constraints. So in Othello, the diagonals are particularly important. So it had features representing those diagonals, configurations of stones along those diagonals, along straight lines, and so forth. But it discovered which particular instances of those patterns it should have in its feature vector. And then it built a very large binary linear value function using these features. So it's got this giant feature vector that's discovered. And now it learns the weights for that feature vector by reinforcement learning. Okay, so this is all doing self-play reinforcement learning with feature discovery. And so what does the reinforcement learning look like? Well, it used a form of generalized policy iteration. So this is an idea that should be familiar to us all by now. What it did was it basically iterated over these phases. So first of all, it played itself a bunch of games. So it has its policies for black and for white, and then it plays itself a few thousand games, using search, by the way, to generate, using a minimax search to generate better play. We'll come to that in a minute. So it generated games of self-play using its current policy. Then it evaluated those policies, basically trying to establish the value function, like who's going to win under this policy? Is black or white going to win under these policies? Which is basically, you can think of it as just a regression problem. It's trying to regress each position to who won in that position. So it kind of does this Monte Carlo learning, figures out, so I've got this batch of play, I start with my policies, I run these games of self-play, figure out who's going to win in these positions, and then improve the policy using that value function. So now improve the policy so that we look at the value function and white picks moves that maximize that value function and black picks moves that minimize that value function to generate two new players for black and white, and then iterate and repeat this process again and again and again. And so the results were very effective, that just from self-play, no prior knowledge apart from this minimal little piece of prior knowledge about what regions of the board should be considered for features, it was able to go off and beat the human world champion Takeshi Murakami 6 games to 0. So it was actually the first program to achieve superhuman performance in any one of these classic games. Okay, so that's Roger Stella. Is this roughly clear? The only part I've skipped over is search, which I want to come back to in a minute. So I don't want to give the impression that search was not necessary in Roger Stella, because it used a minimax search in every position. Whenever it actually played a move, it basically did a big minimax search using the value function which it's learned here to pick the next move. So really the generalized policy improvement is a policy improvement not just based on a one-step max, but on building a large minimax tree using the current value function. That's how it improved the policy. And this was crucial step. Okay. I now want to talk about TD Gammon, which is still, almost 20 years on, the most famous application of reinforcement learning by Jerry Tesaro, who was at IBM Research. And so it's applied to the game of backgammon. So don't really need to talk about the rules, but roughly speaking, backgammon has a board which looks like this, with all of these different checkers. Let's call them black and white, just to be consistent. And the idea is that one player is trying to get all their checkers to move around in one direction, and while the other player is trying to get all their checkers to move around in the other one. And if you roll dice to see where you move your checkers to, and if you land on top of someone else's counters, then they're sent back to the beginning again. So it's like a race to see who can get to the end, but it's a race where there's actually interactions between the players. It's a real game. And what TD Gammon does is it basically has this nice representation of the board. It basically takes the board and it flattens out this board into this state vector here that basically says for each of these locations on the board, how many checkers are there in that location. And it actually has, I think, 6 features for each location, saying, is there one checker here? Is there one white checker here? 2 white checkers here? Are there 3 white checkers here? Is there 1 black checker here? 2 black checkers here? And so forth. So it's got a separate feature for each possible count of stones at each location on the board. And that's the binary feature vector that it uses as an input. What's different about TD Gammon from, I think, any of the other examples we're going to talk about today is that it used a nonlinear function approximator. It used the neural network. And it basically used that binary feature vector as the input to a neural network. The number of nodes in this neural network diagram are not accurate. It used something like, I think, 40 or 80 hidden nodes, and it was, a long time ago you couldn't build big neural networks. And it built a neural network with just one hidden layer, output a value function saying, if you feed in some description of some position here, it will tell you who's going to win the game? What's the probability that black or white will win this game? That's the value function there, the expected outcome at the end of the game. So that was the idea in TD Gammon. It used this nonlinear value function approximation, and then it applied reinforcement learning. So famously, TD Gammon learned just by self-play alone. Again, self-play reinforcement learning. It was basically this neural network was initialized completely with random weights. It was trained completely by games of self-play, and it used a very simple update, which was essentially the temporal difference learning algorithm we were just looking at. So actually use TD lambda, but this is the TD0 update, where we just compute the TD error. It's just what we saw earlier, the difference between what I thought was going to happen in this position and what I then thought. So who I thought was going to win, who I then thought was going to win after one step. Looks at the error between those, adjust the neural network weights a little bit in the direction to correct that error, to make these predictions self-consistent. And perhaps surprisingly, it just used greedy policy improvement. It just picks the action that maximized from white's point of view and minimized from black's point of view, and it never explored. And yet, it always converged in practice, despite all these issues we hear about neural networks possibly being unstable with RL, and these question marks about exploration. It always converged to a very effective solution. So can anyone think why this might be the case? Like, why didn't it need to explore? Yeah?
Is it because the dice roll introduces some randomness into it, so it gets into states it might not have.
Right. So backgammon has dice in it. Backgammon's got stochasticity. And so that means that there's inherently a lot of exploration of the state space. So even if you don't explicitly explore, you still get to see everything. You still get to see all of the different states. And so in this kind of situation, it's not strictly necessary to explore. Can anyone think why it might have been stable when, well, let me tell you that this is not true for other games, that actually in other games, that people were very excited after this, and they tried the same ideas in checkers and chess and Othello and all these things, and every time it diverged and it failed to work. So can anyone think what was special about backgammon that meant that this idea worked so well? Yeah.
Well, I guess the number of states is quite small. The number of actions you can take at any when you're in any state is quite small as well, because you only have 2 moves you can.
It's actually got quite a big state space and quite a big action space. So in backgammon, I mean, you've got 2 dice, and the 2 dice you can move your counters any number of steps according to the 2 dice, and so there's a branching factor for the dice and a branching factor for what you do based on those dice. And there's a lot of states in backgammon, I think, something like 10 to the 40-ish. Now, the answer is actually the same as the previous answer. It's because of the dice. So the dice, the stochasticity in backgammon smooths out the value function. So because you've got randomness, although there are tactics in the game, they're kind of smooth tactics because you don't exactly know what the dice are going to do after this. So there's some randomness of what might happen next and how your opponent might respond after that. And all of this randomness has the effect of smoothing out the value function because you can't precisely rely on taking one particular line and your opponent responding in one particular way and then you responding in one particular way to that because the dice don't let you. Right? Any random event might happen. That smooths out the value function. So backgammon has a very smooth value function which suited neural networks and made them much more stable in the presence of value function approximation. Whereas when people tried to use this in more precisely deterministic games like chess and checkers, it didn't work. And I think you would now need to reconsider this in the light of the recent methods like DQN and so forth, which might address that. Okay, so how strong was TD Gammon? Well, using this, so this representation here, we can think of as zero expert knowledge. We really didn't put in any knowledge into that. But you can also add some expert features based on standard ideas of, there's a few standard features you can use in backgammon. So with zero expert knowledge, TD Gammon, just a neural network, achieved what we call strong intermediate level of play. If you gave it handcrafted features, it reached a more advanced level of play. And then if you combined handcrafted features with a 2-ply minimax search, it achieved strong master level play. And then with a 3-ply minimax search, it achieved superhuman play. So even in backgammon, with this very powerful neural network, at that time it was necessary to actually use a minimax search on top of this value function. So you take this value function, you perform the minimax search, and you use the value function that leaves, just as we suggested earlier. But this is all a long time ago. So Jerry Tesaro actually went back a few years ago. So this isn't super recent. This is, I think, like 2008. Jerry Tesaro went back to TD Gammon and said, well, what would happen if you just ran out these neural networks, train them for longer using better hardware. This isn't even using GPUs or some of the things which people like. You could probably get three orders of magnitude more computation than this used. But all he tried was to continue training using just the raw features with zero knowledge at all. And the different colors here basically show how many hidden nodes the network had, whether it had 10, 20, 40, or 80 hidden nodes in a simple multi-layer perceptron feed-forward network, vanilla neural network. This is the number of self-play training games, up to about 10 million, and this is the performance against the standard evaluation benchmark. And what happened was, if you just kept training this thing, it got better and better and better, and in the end it massively outperformed the version with the expert features. So the story was basically that although expert features were used a little bit in the original TD Gammon, that was just because there wasn't enough computation available. And so now this version here, this magenta one, achieves superhuman level of play with literally zero human knowledge. So it's a nice idea. You literally have a program, plays itself, builds up a neural network that estimates who's going to win in this position, does a little bit of look ahead using that neural network, and you've got superhuman game player. Yeah, question?
Are there ways of reading out the features that this program learned to train the human players?
Okay, so that's a great question. So what happened in backgammon, and it's also happened in some other games, is that it completely changed the way that humans play. So humans then started to look at how TD Gammon played. They're like, oh, I didn't even know you could play backgammon like that. And they discovered new strategies, and they started to figure out different ways to play better. So human level increased as a result of this, not by reading out the features, but observing the way it played at the end of the network. So in general with neural nets, it's hard to interpret the intermediate stages. You can look at it a little bit and try and tease it apart, but I think ultimately humans learn by just watching the way it played and saying, that's a good way to play the game, realizing that it's a good way to play. Okay. So is that clear? So far we've looked at how to do self-play reinforcement learning to achieve high performance in certain classic board games. And now really we're going to focus on how to get a more sophisticated mixture of reinforcement learning and search. Okay, so let's start with sort of the most familiar method. Let's start with basic TD. I'll call it the simple TD algorithm. And let's see if we can understand how to do better than simple TD when we know that we're using look-ahead search. And so we can think of standard TD as looking a little bit like this. That at every stage, we basically have some value function with parameters W. That's our value function estimating who's going to win the game. And the value function at one step gets updated towards the value function at the next step. That's what this arrow means. It's like a backup. It basically means that we look at the value function here, and this arrow means we use the value function here to improve our estimate of the value function here. So this is like we were in state S1, then I played a move, I ended up in this state S2, and I get a better estimate of the value, and use that estimate as my target to update this guy. So that's standard TD learning. And then what we've looked at in Logistello and TD Gammon so far is like this two-stage process, where first of all we learned a value function by self-play, and then once we had this value function, we can do a big minimap search tree using that value function at the leaves. But that isn't necessarily the best way to combine minimap search with reinforcement learning, because it's not helping us find a better value function. The search isn't helping us figure out the value function. We're only it's like we first of all do our TD learning, and then later we do the search. And the question is, can we actually make use of search to make our value function better in the first place, so that during the process of learning, we actually figure out a more effective value function. So simple TD by itself actually has performed well in some games. So we saw in Logistello, TD Gammon, there are cases where it did very well. But there are also games where it does very poorly. So chess and checkers in particular, people spent a lot of time trying to figure this out, and they discovered that TD by itself, back then, who knows if this is still true using more sophisticated function approximators, at least back then, it performed poorly in these quite tactical games. And so, why is this? And I think the answer is it's about the tactical nature of those games, that you really need some kind of search to be able to even figure out the signal and the position. If you just have your features that tell you, how many rooks and bishops do I have in this position, it's not enough information to figure out the precise tactics that lead you to a checkmate. You just can't find checkmates in this game. You can't find the specific tactics that you need to follow to capture someone's piece or to pin them or to do a fork, whatever it is. You need search to estimate the values more accurately. And so the goal is to learn directly from these minimax search values so that we really have this rich search information inherently as part of the learning algorithm. And so can we do this? And the answer is yes. And again, this dates back a very long time. So I'm going to introduce the oldest version first, which is known, I call TD root. And so this idea is, the idea is basically to say we're going to update the value towards our successor search value. So in other words, what we're going to do is when we do our TD update, instead of updating our value function towards the value function at the next state, what we're going to do is update our value function towards our more accurate value function that we got by doing a search. So in other words, if we're in state ST here, what we're going to do is we're going to take a step, we're going to run our really big minimax search, really figure out what the right move is, is there some checkmate available here or not. And then once we've got that much richer value function, we're going to use that as the target to update our original value function. So the reason the arrow comes from here instead of from the top is basically to indicate the fact that once you've run this big search, because it's a deterministic game, once you've run this big search, there's one particular leaf node that actually is on the principal variation. There's one leaf node that was the minimizing, maximizing leaf node, the one which contributed all its value and propagated all the way back to the top. There's one leaf node which is the one that we basically picked out of all those leaf nodes. And that's the one that we used. That value is the one that basically, it's the same as, this value has the same value as the whole search. There's one leaf value that contributed to the eventual value of the whole search tree. And that value is the one that we back up to the root node here. So basically, the right way to think of this is we update our value function towards the outcome of a deep search. But, I'm in this position, I think the black's going to win. Then I take a step, I do a really deep search, and I discover the white's going to win. And so now I'm back here, I say, oh, well, I really wish I could have figured out without doing any search at all that white was going to win. And that would be a very nice value function to have. If we just knew without doing any search that white was going to win. So we're always, you do the deep search, you figure out what you now believe, you get those results and you back them up. Okay? Is that clear? Okay, so that's the TD root idea. So this was introduced by Arthur Samuel back in 1959, and it was the first ever TD learning algorithm. And he applied this in checkers using self-play, and it learned to defeat an amateur human player, which was a big deal at the time, although it's not clear how strong it actually was. So this was great, but it also had some other ideas in there which kind of we now think are a little odd. So it was a bit conflated with all these good ideas about TD and this TD root idea and minimax search. Those are all in there and good, but there were some other funny things that meant it was not quite a vanilla thing. But nevertheless, I think we should attribute all of this good ideas to Samuel. But then, people have taken these ideas and they've progressed them since then. So the first progression is an idea that's called TD leaf. So this idea really has been successful in chess and checkers, so it's worth understanding. And the idea of TD leaf is to basically say, instead of just updating the value now towards the search value of the next step, let's run a whole search now. We want the whole outcome of my search to be made more accurate. So the idea is that at time ST, we're going to run our search. What we'd like is we'd like that whole search to end up giving to output a value which is the same as the value that we got when we did a search at the next step. In other words, if I'm in a position, I run my big search and I think that black is winning, then I take a step, I run another big search and discover that white's winning, then we want to change the whole of this search procedure to say, actually, oh, I got it wrong, maybe I should change the whole of this search to have given a different outcome. We don't just change the value function, we change the whole of the search to give the right answer. And again, the way we do that is we only need to look at the leaf values. There's one leaf in each search which contributed all of the value to the eventual outcome of that search. And that's the only one we need to update. So we update this leaf node here, which was on the principal variation from ST, that's the leaf that contributed, that's the one we chose. We chose this leaf, we chose all these actions down to here, and then this leaf. And all we need to do is to basically update the value of this leaf towards the value of this leaf here, which is the principal leaf that we actually chose at the next time step. In other words, if this value had been a little bit higher, it would have made our whole search value a little bit higher. And so if we ended up underestimating the value, we discovered that our value was a bit higher, we want to change our whole search to be pushed up, and the way we do that is to push up the node that we're actually picking right now a little bit. So that's TD leaf. Yeah, question?
Can I question because I'm still a little bit confused?
Yeah, good.
What's the difference between like research for the like this search, for the case we are in the ST state and ST+1 state? Because I see that there must be some differences here.
Okay, so let me try and explain this clearly. So we're in some state ST, that's our current position. We run a search from this state. What this diagram indicates is what we ended up picking as a result of that search. So as a result of that search,
full search, right? We are doing all the.
We're doing a full width search. At the end of that full width search, we ended up deciding that this red node was the best one, and then white decided to move to this red node, and black decided to move to this blue node. That's what we decided at the end of that search. Then we actually took a real step. We played a real move in the game. We ran another search. So we start now from this red node. We're in a new position. We kind of can share that we've moved on to that red position now. We run a search from that red position, and now we find a new principal variation. So now we run a search, and we again decide that we're still going to move to the red position. We're still going to take this one leading to the blue, and then we're going to take this move leading to the green. So what we can do is we can basically say we want the outcome of this whole search to be moved a little bit toward the outcome of this whole search. So how do we do that? Well, we can say, well, the value which determined my outcome here is exactly the value of this blue node here. The value which determined my search tree here is exactly the value of this green guy here. So all we need to do is to update my value function of this leaf here towards the value function of this leaf here, and that will make my whole search more like the search at the next step. Good, more questions. I know this is confusing, so it's good to get questions.
So what happens at the T+1 step if you decide, when you look at all the 4 lowest nodes, that actually you didn't want to take that blue step, you wanted to go into the other
That would be fine.
direction?
That would be fine. So if you actually went a different way, and this ended up being your node, now we would say, okay, well, we've got some new search over here, which has some new principal variation. We ended up deciding to go there, then there. And so this would then be the node which contributes the value to this whole search tree. This is the minimax value. So the minimax value of this whole search is equal to our value function here, because that's the one we chose. We were minimizing and maximizing all the way down to this point. So now all we would do is update our value of this node here towards the value of this node here. And that's equivalent to saying that we're going to change the whole of our search from this route towards the whole of the search from this successor route. The plus here means that we're doing some search.
So you update the blue one on the left, even though you didn't take the blue one on the right.
Because we want to know how could I have made this was the way that I was searching in this step, and I want to make the way I was searching in this step better. I want to make it more like the way I was searching on the right step. And the only way you can do that, because currently you're in a situation where you're picking this. And so the only way to change that, the only way you can affect this, like if you think about an incremental change, you just get to change things a tiny bit. If you change any of these guys just like a fraction, it's not going to change the minimax value, because these aren't the ones you're picking at the moment. Like if you change any of these other values, it's not going to change. Like if you change this one, even though it's the one you picked at the next time step, this isn't the one that you're picking right now. So right now you picked this guy. So if you want to make the value of this search tree higher, you need to make this particular value higher a little bit. Now at a certain point you'll cross the threshold where suddenly a different node will become better or worse, and at that point you then change that node. But you're always just changing the node which is contributing to the minimax value.
So if my value function for the blue node gets lower, and other nodes from this lower level would become better, then I again have to because I didn't try to remember all the nodes I visited, so I can easily learn. You see my problem?
No.
Okay. So for the blue node, I found that I need to lower the value function.
Yes.
And actually, from this first search on ST3, I would find that another node would be better after the update, the blue node.
Right.
So how can I know which was the better?
Okay. So the question is that we do one update that changes what the principal leaf is, to say this one, and now you want to know what we do in that new situation. Do we need to remember that we used to go to this one? The answer is no, you don't care. Like, you only look at what you're picking right now. So if we update our weights such that now if we search from ST we're picking this guy, we don't need to remember what we did before, because we're now in a situation where when we run this search, we're picking this guy. So if we're in a situation where we're running a search tree, and this is the principal leaf that's contributing its value, again, we just push up or down the value here a little bit. So it's a bit like just think of this as a function approximator that has some non-differentiable boundaries in it. So you've got some function, which is like a linear function approximator, which is like a piecewise linear function approximator. So you can think of this whole search tree as a piecewise linear function approximator. Okay? So it's doing this mini-map, so you get this piecewise linear function approximator, and you use that piecewise linear function as an estimate of the value function. You want to update your piecewise linear value function towards the piecewise linear value function here, and the only bit you need to look at is the piece you're in right now. You don't need to look at all the other pieces. If you get pushed over a boundary between one piece and another piece, okay, so now you're in this other piece, and now you just adjust yourself a little bit on that one. So there is some non-differentiability here, which you need to be careful about. So you might worry that you get trapped in some local optimum or something, which I think is your concern. But it turns out in practice that this is quite effective, for the same reasons that you have a rich space with stochastic data and you're dealing with all these maxes. So we see the same thing in deep learning, methods like MaxOut, where you can have these rich, non-differentiable function approximators with hard non-linearities in there, and yet you can learn very effectively to achieve some, to optimize in this space, because you're seeing every single state you visit in each game is going to take you to, going to make different decisions at these boundaries. I think your concern is something about local optimality. Maybe, okay. All right. I'm going to try and move on, I think. Are people roughly okay with this? There's a slide there, you can come back to it. Notation basically means the plus indicates running a search from this node onwards, and this L plus basically tells us which leaf we've chosen, the principal leaf. So the principal leaf from that route is this L plus, if you choose to come back to us. Okay. So that's TD leaf. So TD leaf worked quite effectively. So it was trained in a program called Nightcap against an expert opponent. And the only knowledge it was given were the piece values. So it had a fairly large number of different features. Like this, again, it had this binary linear value function. Had a fairly large number of features. But it was only told the weights of some of them. It was told the weights of the piece values. It was told the rook's worth 5, the bishop's worth 3, etc. And then it learned all the other weights using TD leaf. And indeed, it was able to tune the piece values afterwards. It was initialized to having some knowledge so that it could get off the ground and do something interesting. And then search, it used a standard minimax search with all the usual standard enhancements. And the results were that it actually achieved master level play after a relatively small number of games. But there were a couple of caveats in terms of how it worked, which was it wasn't effective when it played by self-play. It actually had to train against an expert opponent. And it also wasn't effective when it was started with randomized initial weights of the piece values. It needed to get off the ground first. So we actually went back to this a few years ago, and we came up with what we considered a better method that addressed these problems. But before I do that, I should say that TD leaf was also applied to Chinook. If we go back to this checkers playing program, Chinook, which was the program which eventually went on to achieve perfect play. But before it achieved perfect play, so Jonathan Schaefer and others went back to Chinook and tried to say, well, instead of hand-tuning the weights, could we have done better by self-play reinforcement learning? And so they used TD-leaf to adjust the weights. And again, they kept one material weight fixed, like the value of a checker, they kept fixed to kind of anchor the whole thing and keep it stable. But what they discovered was when they did this, and they just played this thing by self-play and adapted the weights using TD-leaf, that the self-play weights that they learned did even better than the original hand-tuned weights. So again, this was when it was already playing at superhuman level. So this shows that TD-leaf is able to achieve superhuman level in checkers. Okay, but there are these caveats. We want to be able to do more by self-play. We want these algorithms to be more robust and more efficient to learn. And so we introduced a method called tree strap a few years ago, with Joel Vaness and others. And the idea here was to interact with minimax search in an even richer way. And so the idea was to say, instead of waiting a step and looking at a search that you run after one real step, why mix real and imaginary steps? Let's just do everything in imagination. Let's start from, we're in some position. Let's run our big search tree, and let's just look at that search tree and update our value function from the information within that search tree itself. So you only need one search tree now. But what we do is that we basically want to have the following idea, which we want to update the value of every single node in that search tree. We want to basically say, we want the value function of that node to predict what a deep search would have done from that node onwards. So if we can get the value, if we can estimate the value of each node, for example this one, correctly without doing any search, then we think we've got a very good value function. So the idea is that every single node of this search tree, we update the node here towards the search value from that node onwards. And we update the node here, the value of this node here, towards the search value from that node onwards. And we do that for every single subtree within the whole search tree. We basically say we want the value function to correctly predict what the whole search would have done from that node onwards. And we've got this very rich data. Every single time you run a search, you generate millions of minimax values. So the idea was to use those minimax values effectively rather than just taking one value and throwing away the rest of the search, as we did in TD-leaf and TD-root, where we generated this whole search, but we only used one value from each search. So in tree strap, we use all of the information from the search as targets to make the values better at every single node in the search. Is that clear? I'm getting more nods for this one. Is this less confusing than TD-leaf? Okay. So this method is quite effective. So the program that Joel tried it in was called Leap. This is a binary linear value function again, using around 2,000 features. These were handcrafted features. But they started with completely random initial weights, so we didn't give any information about piece values. And then adjusted those weights by tree strap. And after adjusting the weights by tree strap, we then played it on the standard online chess server to see how it played. It won 13 out of 15 games it played against international masters. So this, I think, is it's also been used, I believe, in some. So the chess programming world is very closed shop, but we at least heard from one of the strongest programs to say they've got much better results in chess than this using tree strap. So I think it's a method that can go further. But it was effective in self-play and effective in random initial weights. And the reason that it tends to be more effective is because it doesn't have this mixed backup, wherein these previous methods, you're kind of mixing between doing this big search yourself by kind of imagining what would happen, and then looking at some sampled action, some random action that was taken in self-play, and mixing these two types of backups together isn't necessarily the best idea. So in tree strap, we just do something simpler, which is to generate a big search, update the search from the search itself. So update a shallow search from a deeper search. That's the way to understand it. You want your shallow search to give you the results the deep search would have done, with less computation. And the limit of that is you want your value function to directly give you the results the deep search would have given you without doing any search at all. Okay. Right. So, that's the end of that sort of mini section. Any questions on those? Successfully confused everyone in the room with the TDD. Yeah.
Sorry, so you never mentioned anything about conversions. Is there any, or did you deliberately do that?
So let me say some things about convergence. Okay. So minimax search converges on the minimax value function. If you search deep enough, it will eventually, if you can get to the end, it will converge on the true minimax value function. Self-play reinforcement learning. I mentioned Michael Littman's seminal work. So he talks about convergence of certain standard RL algorithms, Q-learning and so forth, in the context of table lookup value functions, and shows that these self-play reinforcement learning algorithms do converge to the minimax value function. So that's what we know about convergence. I would say for all of the practical examples we've looked at, we're outside the scope of what is known to converge. And in some cases, we're using methods that we know may diverge, like in TD gammon. We know for a fact that using a neural net with self-play can diverge, and yet it worked in TD gammon. So these methods here, empirically, what's important with all these methods, like this approach here, is that you have to ground it. You can't just learn from your own search without grounding it. You can't just keep running on your own big search tree without seeing any real data. And the way that you ground it is you have to get to the end of the game. You have to interleave this with real outcomes. You have to see some real outcomes in your search tree at some point. Otherwise, you can end up just kidding yourself into believing that you can update your value function towards what you searched it to, and then just keep doing that, and eventually you'll drift away from reality. So you have to have some reality in there, which means you have to do this from all kinds of positions. The route has to be at all different stages of the game, and you have to have sufficient number of game positions that actually see the end game, the outcome of the game, to ground this. Okay, that's an empirical concept. Right. So I just want to talk about simulation-based search again. So in the 2 lectures ago, we had a lecture where we talked about simulation-based search. We talked about this idea that we can achieve high-performance search by running simulations and applying RL algorithms to those simulations. And so we had this idea that you can basically start at some root state, like the current position, generate simulations from that root state, apply, say, Monte Carlo learning to the simulations that you run from that root state, and get a very effective high-performance search. And so now what I want to do is just talk about that again in the context of what we've learned about self-play. So in that lecture, we were really mostly talking about single-agent case, but I used the example of Go. And so we've seen that you can do something like run your simulated experience. Now we're going to simulate those games by self-play. So in other words, we're going to start from state ST. We're going to run out games where white plays a move using our policy, black plays a move using our policy, all the way to the end of the game. And we're going to learn from that experience by applying, say, Monte Carlo learning or TD learning or any of the updates we've seen so far. And when we do this with Monte Carlo control, we arrived at an algorithm which we call Monte Carlo tree search. And in the last lecture, we saw how this is very effective in the game of Go. I just want to mention that the most effective variant in games to date has been something called the UCT algorithm. And the UCT algorithm is basically Monte Carlo tree search with, instead of doing something naive like epsilon greedy, it uses a slightly more sophisticated exploration strategy, which is to say at every node in the search tree, it treats as a bandit algorithm and applies the UCB algorithm at every single node in the tree that we saw in the last lecture. So we had this bandit algorithm in the last lecture where you can decide which arm to pull so as to make sure that over time you explore all the different arms in the way that gets you the most money from your machine or whatever it is. And so this idea can also be applied in a Monte Carlo tree search by treating each node in the tree as its own bandit and basically pulling the arm, picking the action, is basically now means selecting the child that is most likely to win the game. And so you basically get to explore all of the children systematically in a way that encourages you to visit the parts that are most successful so far, while still exploring everything. So this basically guarantees that you explore all parts of the tree very, very systematically, but in a way that still gets an awful lot of the simulations go down the principal variation, the best part of the search tree. Okay, that was a little aside. So the UCT algorithm has been very effective in many games. So we saw last lecture Go. There's also games like Hex, Amazon's, Lines of Action, these other games which, roughly speaking, any game which has a large branching factor or where it's hard to construct a value function, it turns out that these Monte Carlo tree search can dramatically outperform what was achievable with standard minimax search algorithms like alpha beta. Now, if you take the UCT algorithm, someone asked about convergence, you take this UCB algorithm and you run it, you apply it with self-play, this has been proven to converge on the true minimax value for that game. So you start knowing nothing about the game, you just run these simulations, self-play, I guess you know the rules of the game, you run these simulations from your current position, and you learn by self-play, applying the Monte Carlo control, eventually you will find the minimax optimal values in any of these games. And even if you don't reach convergence, you can still get very good performance in many challenging domains. Okay, I just wanted to point out that in many games, you don't even need to do something so sophisticated. So in many games, you can use simple Monte Carlo search, this idea of just running rollouts and picking the best action from those rollouts. So Scrabble and actually backgammon are two examples of this. Scrabble we'll see in a moment. Backgammon, it turns out that the TD Gammon guys, Jerry Tesaro, when they went back to TD Gammon, they discovered that they could do better using Monte Carlo search than using an alpha beta search in backgammon. So that was some later work. So the final part of the class, I'm going to talk about two imperfect information games, which are Scrabble and poker. Both of them build on Monte Carlo search ideas to achieve success. So basically the part we're dropping is this sort of minimax search via brute force alpha beta kind of depth first search. And instead we're going to consider these self-play approaches to search based on simulation-based search algorithms, Monte Carlo search, Monte Carlo tree search. Okay. Right. So let's consider the game of Scrabble first of all. So in the game of Scrabble, the first program to achieve superhuman performance was a program called Maven. So the idea of Maven, so first of all, I mean Scrabble actually, you might think that it's trivial to make a computer program that's better than humans because you give it the perfect dictionary and a human could never have a perfect dictionary and therefore anything with a perfect dictionary must outperform humans. Turns out not to be true for two reasons. The first reason is that the top human players memorize the entire dictionary. And the second reason is that not just the entire dictionary, they memorize all the anagrams and all the hooks that you can get from one word to the next one. The second reason is that there's actually a lot of strategy in the game of Scrabble that humans are very good at and naive alpha beta search or something like this is very poor at. And the strategy basically comes from the fact that you don't just want to greedily play the move that gets you the most score, you want to make sure that you leave letters on your rack after you've played your move that give you the most potential for score later on in the game. So if you leave the blank on your rack, you're probably going to get a bonus 50 points in the next move when you then get a 7-letter word and do even better. So there's a value to keeping things on your rack, which means you can use these good letters, the S and the blank and so forth, to do very well in your next turns. So what Maven did was essentially a reinforcement learning approach. So this is the one game we're going to consider where we won't just look at the outcome of the game, but rewards along the way. So in Scrabble, you basically get a reward along the way, which is the score at every single move. So you play your word down on the board, you get some score, and then you get some immediate score, but you also have a value function, which depends on how good your rack leave is. Technically, it also depends on the board position as well, but Maven ignored that and just said, let's come up with some general values that say, how good is it to leave an S on your rack? How good is it to leave a blank on your rack? How good is it to leave a Q on your rack? All these kind of things, and sort of independently of the actual position. And then what they did, so this is Brian Shepherd a few years ago, what he did was to build a binary linear value function again. And the features this time are like these letters that you leave on the rack. So there'd be one feature saying, have I got a Q in my rack? After I play my move, have I left a Q in my rack? Have I left a Q and a U in my rack? Have I left 3 I's on my rack? These kind of features, and they're all 1, 2, and 3 letter combinations. And so, you might naturally consider that leaving a Q by itself on your rack should have a very bad value, but leaving a Q and U together could have a very good value because it lets you play this high scoring Q. And then, much like Logistello, what Maven did was to learn the weights for this binary linear value function by this policy iteration approach, where we ran batches of self-play games, start with some policy, run a batch of games against itself, evaluate those that using Monte Carlo, i.e. regressing to the game outcomes to figure out the value function, and then using that to improve the policy and iterating again and again and again. So it learned this value function. So it's got a value function. And then it used this value function in a search. And the search was the simplest possible Monte Carlo search you can think of, which is just to imagine n steps of self-play. So the idea was to basically, you've got some rack lead, and now you've got the position you're actually in. So what Maven did was, if you want to know, how good is it to play this particular word in this particular location, what it did was it would actually, in its mind, it would play that word, and then it would run a bunch of rollouts to see if it just randomly picked letters from the bag and rolled out those the game for some number of steps after that, played for itself, played for its opponent, played for itself again, and played for some number of moves, and then it would evaluate the resulting position by the score for those n steps, plus the value of the rack leave at the end of it. So basically, roll out this position, and then truncate and use the value function after n steps. So it didn't go all the way to the end of the game, just for computational reasons, largely. Is that clear, the idea? So it basically rolls out games from this point onwards, considers a move, rolls out, it's like, I could play the word fox over here, so I play fox, I now roll out, say, 100 different games, starting from this position with fox on the board, play 100 different games, see what score I got in those 100 games, take the average of those games, the scores in those games as my estimate of the value of playing fox. So I add up the scores along the way when I play fox, after I play fox, and then truncate the game and use my value function. It also had a specialized endgame search, but I won't go into that here. Okay, so how did it do? So I really like this position here. I think it's a really fun story. So this was the moment when humankind realized that they were defeated at the game of Scrabble, where there was this position getting quite complicated, and this was against the world champion, Adam Logan, to decide whether humans or computers reigned supreme. So Adam Logan was the reigning human world champion. And they reached this position where Adam Logan was winning this particular game by miles, and he thought he was, had a comfortable win. But it turned out that Maven had basically been rolling out all these simulations, and it had figured out it had one chance to win this game, which was to fish for this particular word, which would give it a 50-point bonus by playing out all its letters and complete the game and get all the bonus points you get from finishing the game as well. And it fished for this combination, and it picked up the letter, and it played this word mouthpart, which is a 9-letter word, which means you can only get 7 letters in Scrabble, which means it had to play over 2 existing letters. And it fished for this opportunity and saw that this was the only way to win the game, and indeed it got the word that it fished for, played this game and defeated Adam Logan, and this was one of the games that he used to win the World Championship. I don't even really know what a mouthpart is. I mean, that's Scrabble for you. Anyway, they ran some analysis of this game afterwards with some human experts rolling out different games, playing out amongst all the different possibilities. And they estimated that Maven only made an error rate of 3 points per game. But basically, if you looked at the entire game that Maven played out, and they typically score maybe about 400 or 500 points in a game, that if it had played perfectly throughout that game, it would only have changed its expected score that it could have got by at most 3 points in any one of those games. So it was very, very close to perfect. Caveat, I suspect this result is bogus, because I'm pretty sure that actually you can do better than naive rollouts by doing a Monte Carlo tree search and actually looking at the contingencies of what the opponent played and then what would have happened after that. So I suspect a real strong search program, which someone might one day build, would actually do better than what humans currently think is optimal.
So did it not have any sort of concept of trying to avoid leaving the opponent in a position where they could easily get a triple word score or something?
Well, that appears in the rollouts. That appears in the rollout. So if you basically open up a triple word score, like you play Fox, and it gets you a big score, but it leaves the triple word score open with the X or something. And now, in all of your rollouts, the opponent's a lot of those rollouts, the opponent will be able to play on that triple word score using the X. And so that's what shows up this. That's what gives the big benefit. So that's what the Monte Carlo search identifies. It's starting from the current position and it's exposing the weaknesses of each of the moves that you play, and that comes out in the rollouts. So that's exactly why it's effective. I just wanted to say one more thing, which is technically Scrabble is an imperfect information game. Right? We don't know what's on the opponent's rack. And so far I've completely ignored that part. And Maven completely ignored that as well by doing the most naive thing which you can do, which is just to randomly sample letters for the opponent's rack from the letters that are remaining in the game. And so that's very naive because the opponent actually reveals information about what's on their rack by the way they play. But Maven basically ignored that. But more recent programs have actually made some use of that information. But still, it's playing pretty well already. Okay. So that brings us on to imperfect information games. And I want to talk about some recent work, actually by someone who was sitting in this class the last time around when I gave these lectures. And they're now on the list of success stories in games for RL. And this is an approach called Smooth UCT. So this builds on the Monte Carlo tree search approach that we've seen, but it shows how it can be extended to imperfect information games to get state-of-the-art results and achieve superhuman play in the game of poker. And so the way that this was done is you basically need to consider games, these imperfect information games, where you've got information that needs to be hidden, you've got these states, you need to figure out what your opponent's got, you need to play in a way that doesn't expose your own strategy too badly so you can be exploited. And the approach which was used was inspired by another technique from game theory, which is called fictitious play. And the basic idea was that the agent, when it's doing this self-play, it doesn't just learn how to play against the opponent's current behavior. It learns how to play against all the ways that we've observed the opponent play so far. So basically averages over all of the opponent's behaviors that we've seen so far, and it learns a best response to the opponent's average behavior, not its current behavior. So this leads to a much more robust approach to reinforcement learning. So let me prefix that by saying that if you naively take Monte Carlo tree search or UCT or one of these methods for a sophisticated self-play reinforcement learning approach that we believe works so well in all these other games like Go and so forth, and you apply it to an imperfect information game, it blows up. It doesn't work. It diverges. You don't get to a Nash equilibrium. Okay, but this approach really does find a Nash equilibrium strategy. You can see this when you apply it to small games, small variants of poker. It really does find a Nash equilibrium. So the idea again is basically you see some opponent strategy, you see how your opponents are playing. So you're running these games of self-play, and all you do is you count how your opponent's playing, you count the actions that they take so far, and you remember them. So you basically get an average strategy. You average over all the ways that you've seen the opponent play so far. And that gives you your average strategy. It's just the average of all the things your opponent's done to date. And now, what you do is you mix together a standard UCT algorithm, this basically your Monte Carlo tree search that acts greedily with a little bit of exploration, and you mix that together with something which is behaving optimally against this average policy. So you sometimes behave in a way that's robust against all of the things that you've seen your opponents do so far in your self-play games. And this is enough to stabilize the algorithm because it makes sure that your self-play cycles can't just take you off in some strange oscillation that takes you away from the Nash equilibrium. So the way to think about this in general then, so this is how you build search trees in these imperfect information games, is we need to think about the different players in the game. We need to think that each of the players actually sees different information. And so intuitively, they each have to have their own search tree. Each player basically sees different observations. They see their cards. So I see my own cards, so I'm kind of in a different node in this search tree. So to player 2, you see some other cards in his search tree. And so what we need to do is build a Monte Carlo tree search approach, or any other tree search approach for that matter, which is able to effectively learn about a set of search trees. And we want to share information amongst these search trees such that basically what we have is each player is picking their actions according to their own search tree, but now those simulations are used to update the statistics in someone else's search tree. So each player is basically figuring out their best way to play from the experience they're observing of other players play. during self-play. So we've got the self-play procedure. Everyone builds their search tree of everything they've seen so far, and they figure out the best way to play in the context of the simulations they're seeing from everyone else's search trees. So this is the approach which is necessary and effective in imperfect information games. So the idea then is to take this smooth UCT algorithm and apply a smooth UCT search to basically estimate the statistics of every single one of these nodes of this search tree separately. Each player builds their own smooth UCT search, picks actions according to this formula we just saw, and then this approach was actually applied in the computer poker competition last year. And I should mention that in the game of poker there was a big story maybe about 2 months ago which came out in Science, which showed that Michael Bowling at the University of Alberta actually came up with a perfect player for computer poker. By perfect, it means that it really, really was so close to the Nash equilibrium solution that you would need like 1 million years of play to be able to differentiate, to tell that it wasn't playing Nash. But it turns out that this very simple agent here that we've just described using self-play reinforcement learning techniques actually outperformed the perfect player at the computer poker competition, so outperformed all of the University of Alberta bots. And the way it was able to do this was by exploiting self-play reinforcement learning. So even though it couldn't beat one-to-one this perfect player, it can actually exploit the other players more effectively. And the reason it can exploit those players more effectively is because it's really learning in the presence of self-play. Self-play helps it to see the positions which are interesting as the search progresses. It kind of spends a lot of time considering situations that really can occur when players are learning these different strategies. And so when those play situations then occur in real games, it's already figured out how to deal with them. So it generalizes better, this self-play approach generalizes better to real games against other players than a systematic search as was used by this perfect player, which you can think of as the natural extension of minimax search to these multiplayer imperfect information games. Okay, sorry, I know that was a lot of information about imperfect information all at once. But any questions about this part before we close? Okay. So I just wanted to conclude by putting up this one slide, which kind of summarizes by going over all of the different games that we've looked at so far: chess, checkers, Othello, backgammon, Scrabble, poker, and asking, well, what's the recipe? What's the recipe for doing well in these games? What was the same about them all? Were there similarities? Could we pick out things which were important to be effective? And if you were to go off and try and achieve superhuman performance in one of these games, what would you do? And so this is looking at the best reinforcement learning, or the first best reinforcement learning agent in each case. And we see that the input features in each case, it started off with some input features which were binary. So in chess, we had these piece value, do I have this piece on the board? Am I in this piece configuration? Do I have this pawn structure? In checkers, we have pieces. In Othello, we have these disk configurations. In backgammon, we have the number of checkers in each position. In Scrabble, we have the letter configurations on the rack. And in poker, we use these card abstractions, which I didn't really talk about. And then in each case, we built a value function on top of these input features. Most of the examples used a binary linear value function. TD Gammon used a neural network, and I expect to see more work in this direction in the near future. Now we have more effective computational methods for deep learning, and also more stable RL algorithms for deep learning. And then in each case, there was some reinforcement learning algorithm which was applied, either tree strap, TD leaf, Monte Carlo, TD, and we can think of these as all living in the family of TD lambda. In some sense, we know that Monte Carlo is an instance of that's TD1, we've got TD0, we've got these minimax variants that use TD leaf and tree strap, but they're all in the TD family. And then training, we see that this self-play idea, this idea of actually trying to figure out the best way to find the best policy by not training against some fixed opponent, but by training against ourselves and adapting, co-adapting until you arrive at something approximating a Nash equilibrium, has been extremely effective across all these games, as well as being sort of intellectually appealing. If you can just set this thing off to play itself and then it comes back and beats your expert. And then on top of this, search is crucial. search is crucial. You need in many of these games to exploit the tactics of those games using alpha-beta search, Monte Carlo search, and some Monte Carlo tree search, different variants of these approaches all put together. I should close by saying, having said that, we should always question our assumptions. So I think I've strongly given the impression and advertised the fact that search is necessary in many games with a lot of tactics. And I, for years wrote these papers saying, well, if you play in a game of Go, it's necessary to use search. You have to search from the current position because you can never build a value function approximator that's expressive enough to capture all the nuances of what happens in this vastly complex game. Except that then we just did that a few months ago, and we built a very deep neural network which was able to play Go immediately just by reading out this neural network, as well as a Monte Carlo tree search with a million simulations. So you should always question your assumptions. It's possible sometimes to do very effectively using the right kind of value function approximation. And there's this well-known trade-off in games, which is between search and knowledge. That you can put in a lot of knowledge into your input features, into your value function by learning, or you can acquire that knowledge through search by searching deeper and deeper and deeper. And these things play off against each other. And there's two ways to make progress, which is to search deeper or to learn better. And I think they're both flip sides of the same coin in some sense. Okay, that's it. So thanks very much for coming to the course, and hope you got something useful about it and continue to do great things with RL. And cheers.